Okay, so this is the direct comparison test. It says, what I'm really concerned about is this series that has coefficients an. I want to know, does that series converge or does that series diverge? But we are going to select another series one that we know about to compare it to. So to make this useful, the series that we select, the series that we get to choose, the Bn series, is one that's really, really similar to the An series, but maybe it's simplified in some way so that we can use a different result, right? Maybe the Bn series is a geometric series, and we know if it converges or diverges. Maybe the Bn series is a telescoping series, and we know if it converges or diverges. Maybe the Bn series is a P series, or maybe it's another series we can solve with an integral test. So that way we can figure out Bn, and even though we can't figure out An, because An is not a geometric series, it's not a P series, it's not telescoping, it's not an integral test, we can still figure out whether An converges or diverges just by the comparison. And so the first statement says, if all of the terms Bn are greater than the terms An, and the series Bn converges, then the series An must converge as well, because every single term is less than the corresponding term in the Bn series. So it can't diverge to infinity. On the other hand, if the Bn terms are every one of them less than or equal to the An terms, and your series Bn diverges, like diverges to infinity or oscillates or whatever, then your series An must diverge as well. So here's what that looks like. We say, determine whether the following series converges or diverges. Well, in this case, this is my series that I care about. So I'm going to call this An. And An is 1 divided by 2 plus 3 to the n power. And we get to choose a series of terms Bn that are going to look similar to the An series, but it's going to be simplified in some way so that we can figure out whether this Bn series is going to converge or diverge. And so what I'm thinking is, what if we got rid of the plus 2? What if every term in my Bn series was just 1 over 3 to the n power? Then this series does it converge or diverge? This converges, but it doesn't converge to 0. This is a geometric series, because 1 divided by 3 to the n is the same thing as 1/3 to the n. This is a geometric series. the geometric series is the series where all the terms look like r to the power n. And the geometric series converges as long as the absolute value of r is less than 1. In this case, r is 1/3, and 1/3 is less than 1, so it converges. However, that is just the series that I selected. We determined that the series I chose is a convergent series. To use the direct comparison test, we also have to show that every term an is less than the corresponding term bn. So we write an is less than bn because 1 over 2 plus 3n is always less than 1 over 3n. So the original series that we care about converges according to the direct comparison test. Or you could just say by direct comparison if you want to. And so whenever I ask you one of these questions on a test, I don't want you to just say converge or diverge. Otherwise, anyone could just walk in and make a 50 on the test without learning anything about calculus 2. It's not just a yes or no question. It's supposed to be a question where you kind of provide some kind of explanation, like show me with your work on the page that you understand why we are so certain that this original series is going to converge. And to do that, you have to show me that 1 over 3 to the power n is a geometric series, and you know that it converges because 1/3 is less than 1. And you have to show me that 1 divided by 2 plus 3n is always less than 1 over 3n, and that you are using the direct comparison test. Make sense? Okay.
So because of the comparison test, since it's less than, it converges, but then if it or when we find...
This is the case we just found. Is that all of the terms an were less than bn, and we found that bn converged. That means an must converge as well.
Oh, so we have to prove that bn converges too.
Yeah, you had to prove both of those two things. If we had found that bn was less than an and bn converges, that doesn't prove anything. Mm-hmm. And likewise, if you found that an was less than bn and bn diverged, that again wouldn't prove anything. So you got to read the fine print. So the direct comparison test doesn't always work. I'll show you an example. When I look at this and we say, okay, my original series is looking like 1 divided by 2 plus square root of n. An obvious way that we might want to compare this series to something else is we could say, I'm going to compare it to 1 over square root of n. Because that would be the same as 1 over n to the 1/2 power. And this would be a p series. And this p series converges or diverges? Remember, a P series is a series that looks like 1 over n to the power p. And a P series converges if p is greater than 1. And a P series diverges if p is less than or equal to 1. So whenever I have p equals 0.5, is this going to converge or diverge? Yeah, this is a P series that diverges. Of course, that is just the series that I selected to compare against. This doesn't say anything necessarily about the original series, unless I can also show that AN is greater than every corresponding BN. Because that way, if B diverges and A is greater than B, that must mean that A has to diverge as well, according to the direct comparison test. But you'll notice 1 divided by 2 plus square root of n is actually less than 1 divided by square root of n. So we cannot conclude anything. Right? I still don't know if the original series converges or diverges.
Can you over manipulate like your BN so then like you get something that's wrong? Like if you took away like can you make it look like something so far, like if you took out like, I don't know how to do it on this one, but like you would conclude that it actually converges, and then you would say that it's less than, so AN would also converge, but then that wouldn't actually be right.
I mean, so if you're not making any mistakes, if you're doing everything correctly, then this one actually diverges. But what I'm trying to show is that the direct comparison test on its own is not enough to prove that this diverges. I know it diverges because of other methods, right? We're about to talk about that in a second. But I'm just saying the direct comparison test by itself is not enough to show that this diverges. It really does diverge, but we haven't proved it yet. And like if you wrote this down, or if you write, I think that this series diverges, but I can't prove it, then you know that's not going to be enough on a test to get full credit. So when the direct comparison test doesn't work, one of the options you have is the limit comparison test. And this is a little bit more difficult to understand, but the idea is, number one, you calculate a limit and it's the limit as n approaches infinity of the ratio of AN to BN. So the series you care about is on top. The series you're comparing it against, the B series that you pick yourself, that goes on the bottom. So when we take a ratio of these terms and take the limit of that ratio as n approaches infinity, we're going to get a limit capital L. And if the series B converges and L is 0, or L is just any old finite real number, then that implies your series A, the one you care about, converges. And the other conclusion you can make from this limit comparison test is if your series B diverges, and the limit is greater than 0. So it's not 0, but it's strictly greater than 0. It could be a finite number, or it could be infinity for all we care about. Then your original series A diverges. So when you take this limit, there's three options. There's three things that might happen when you take the limit. Either this limit goes to 0, or this limit goes to infinity, or this limit converges to some finite number. If that limit comes to some finite number, that means the ratio between your series A and some series B approaches a finite number, then they're either going to converge or diverge together. If it's 0 or infinity, the case is a little bit more sophisticated, I guess, a little bit more complicated. If L is 0, then you can only show that A converges when B converges, and if L is infinity, you can only show that A diverges when B diverges. The limit comparison test is a lot more powerful. The only time it will leave you with an inconclusive is if like B converges and L is infinity, or if B diverges and L is 0. Then your limit comparison test isn't going to give you an answer. So if you're interested in why this works, I've got that typed out here, and I passed out you these typed out notes too, so we can just quickly discuss what's happening. You start off by supposing that these terms are both greater than 0. They're both positive. And that's not necessarily the case every single time. But if you wanted to know about the convergence of a negative series, it's going to converge when the positive series converges, right? Like the plus or minus sign doesn't matter. You just factor out the minus sign. So suppose that's true. And you take this limit. As long as this limit is not infinity, meaning whenever I say strictly less than infinity, I'm just saying not infinity, then there would exist some capital N, that's just any large positive integer, such that this ratio is going to be less than L plus 1 for every lowercase n greater than n. That's just, it follows from our definition of sequence convergence that we talked about in like 4.1. This inequality, if I were to take both sides of, or all three terms in this inequality and multiply everything by bn, then I get this inequality. And if we disregard the first capital N terms on both sides, remember I can discard as many starting terms as I want from a series, and it doesn't change whether the series converges or diverges. It's only the last infinitely many terms that decide that. I can throw out the first 3 terms or the first 3 million terms, it doesn't matter. So disregard those first terms, then you can use a direct comparison test to say that, well, if Bn converges, then An must converge because it's less than some multiple of Bn, and we can always just divide the Bn series by L plus 1, and of course dividing by a constant doesn't change whether it converges. That's one part of the limit test theorem. That's the first part, is what we've proved so far. To get the second part, the converse, you just take the reciprocal of everything. So in my inequality, instead of taking the limit of a over b, if I take the reciprocal, well then that limit would be 1 over L. It's a reciprocal, so that again, it's a constant, finite, real number limit. And then you use the same kind of argument to show that having A converge implies that B converges, and if A converge implies B converge, then B diverge implies that A diverges, right? It's a if and only if, both ways kind of thing. So that's a little bit of explanation, but you don't need to know the explanation, you just need to know what exactly the criteria are for using the limit comparison test. Okay, determine whether the following series converges or diverges. And this is the same series I showed you a moment ago when the direct comparison test did not work. But now, let's define an as 1 over 2 plus square root of n. And then, like we did before, we'll say that bn is just 1 over square root of n. So this is something that's really similar to a, but it's simplified a little bit. And that is 1 over n to the 1/2 power. And we know that this diverges because it's a p-series with p equals 1/2 less than or equal to 1. And then we say, I'm going to take the limit as n approaches infinity of an over bn. And that would be the limit of square root of n divided by 2 plus square root of n. And if you think about the limit where n is approaching infinity, 2 is staying the same size, but square root of n is approaching infinity. So this limit is going to be what?
Infinity over infinity.
Mm-hmm. But specifically, these infinities are growing at the same rate. Like I've got square root of n divided by square root of n plus 2. So imagine n is the number 1 million. Right? It's a really, really, really big number. The square root of a million is like 1,000, right? What's an even bigger number? A trillion? What if n is a trillion? If n is a trillion, then the square root of a trillion is a million. So it's like a million divided by a million and 2. What am I getting closer and closer to? 1. This ratio is getting closer and closer and closer to 1. Another way to see that maybe is you could divide the numerator and denominator by square root of n. Like do the same thing to the top and bottom of this fraction, divide by square root of n. Okay, so now when I take the limit, I've got 1 in the numerator divided by 1 in the denominator plus 2 divided by square root of n. And as n approaches infinity, the square root of n approaches infinity. So what's 2 divided by a number that's arbitrarily large, just approaching infinity? That 2 divided by square root of n is approaching 0 in the limit, so that this limit is 1. And since L is equal to 1, the series that I originally care about diverges by the limit comparison test. When I was a Calculus 2 student, I thought these problems were really weird because up to this point in all my math classes, you're like trying to solve for a number, right? Like you want to know what is the integral, and you will have like a number that's like 45 at the end of the problem. But these questions, in practice, you don't actually know what the value of the series is. In fact, nobody knows what the value of the series 1 divided by 2 plus square root of n is, right? It's just not something humans know. It's probably an irrational number, first of all, and so you can't ever know all infinitely many decimals of precision, and it's not, to my knowledge, related to like pi or e or any of the other irrational numbers we know or care about. So it's bizarre, and if you want to approximate this, the only way to approximate the value of the series is just to add up partial sums, right? Just like take a partial sum with like 1,000 terms. But in this class, what we really care about is just, is it going to converge or is it going to diverge? We don't know until we prove it one of these tests. So here's an interesting one. Determine whether the following series converges or diverges. The series is natural log of 1 divided by n squared plus 1. So what do you think we should compare this series to? We know that I'm either going to use the direct or the indirect comparison test. And in either case, I'm going to end up having to choose some kind of series to compare it to. So what should I say Bn is?
ln of 1 over n squared.
Okay. That's not a bad idea. So do you know, for each one of these, is an going to be less than bn, or is an going to be greater than bn?
I think an will be greater than bn.
Yeah. So the natural log function is a strictly increasing function. And so if I have a larger argument in the natural log, it's going to end up being a larger natural log. So we know that an is going to be greater than bn. And so I'm only going to be able to get something useful out of this comparison if bn converges or diverges? Diverges, right? So if an is greater than bn, I'm looking for bn to be something that diverges. And so I wonder, what we can do here. We'll consider the series Bn and I know properties of logarithms. Like this is the natural log of n to the negative 2 power. And if I've got negative 2 powers inside of natural logs, I could rewrite that as negative 2 times ln of n. Aha. This is an important thing to discuss. Do you notice how I have a negative series? Like every term in this entire series is going to be negative, because natural log of 1 is 0, natural log of 2 is a positive number, natural log of 3 is a positive number, and so on. But I'm multiplying by negative 2 every time, which means that my entire series is going to be negative. This is where this is where maybe part of the hypothesis here of the limit comparison test matters. One of the things we suppose when we use the limit comparison test is that we're dealing with series that have positive terms. That's an greater than 0 and bn greater than 0. So I told you one of the things we could do if you ended up with a series that had negative terms is you could just take the negative of those terms, right? And then see what happens to the series. So in other words, make that negative natural log of 1 over n squared, and then we would get this, because two negatives make a positive. But now, if I change those to negatives, for every an, if I compare it to bn, would I still say that an is greater than bn? So this is really tricky to think about, but bn is actually positive when I put that minus sign in front. Because if I have 1 over n squared, that's like n to the negative 2 power. And then a property of logarithms tells me I could take the negative 2 power outside of the logarithm and multiply. So I have negative times negative 2, which is positive 2 natural log of n. And so positive 2 natural log of n is going to be growing as n grows. It's actually going to diverge as a series. The an, however, is actually going to be shrinking as n grows, because I've got 1 divided by n squared. That number is getting smaller. And so what we're going to find is that an is now less than bn. For all n greater than 1. Because just think about it. If n is 2, that's 1 divided by 4 plus 1. It's the natural log of 1.25. b, however, would be the natural log of 2, which natural log of 2 is greater than natural log of 1.25. Okay, so now what I'm looking for is to say if an is less than bn, I'm rooting for bn to diverge or converge. Converge or diverge? Converge. I'm looking for bn to converge. And then if bn is trying to converge, does bn converge? No, because if I'm adding up natural logs, that's only getting bigger and bigger, and bn diverges. So this comparison tells us nothing, unfortunately, because the way we chose our an and our bn is greater than an, but bn also diverges, so it doesn't really help. So I couldn't choose natural log of 1 over n squared, and the reason is because that would be negative, and I can't compare negative series. That's not allowed in my limit comparison test. Whenever I tried to fix that by putting a minus sign in front, that makes the limit comparison test a valid test, only it didn't really help us. So I know which series we should compare this to. Do you have another guess for how we should do this? I'll give you 3 guesses and then I'll just tell you the answer. Okay. What we need to end up comparing the series to in the end is 1 divided by n squared plus 1. Oh, sorry, I don't think I need the plus 1. I think I just need 1 over n squared. Because adding the plus 1, that would definitely diverge. So let me try this with which is 1 over n squared. My series is going to look like this. Does this purple series converge or diverge?
Converge.
Yes. How do we know that this converges?
It's a p-series where p is greater than 1.
Perfect. Because this is a p-series where p is greater than 1. So since Bn converges, one thing I could figure out with the direct comparison test is like if An were less than Bn, then I could use the direct comparison test to claim that An converges. But I'm not 100% sure how I'd even show that. So let's not use the direct comparison test, because I don't know how to do that. Instead, let's use the limit comparison test. And the limit comparison test says, let's take the limit as n approaches infinity of the ratio an divided by bn, and that would be the limit of natural log 1 over n squared plus 1 divided by 1 over n squared. What is this limit? Okay, in the limit, as n approaches infinity, 1 divided by n squared goes to 0. Natural log of 0 plus 1 is the natural log of 1, which is 0. So the numerator is 0. What about the denominator? That's 1 over n squared, that's 0. So I've got 0 divided by 0 in my limit, right? That's called an indeterminate form. So I can use L'Hopital's rule. And L'Hopital's rule says let's take the derivative of the numerator and the denominator separately, and then try the same limit again using just the derivatives. I'm going to give myself a little bit more room, because for the numerator, we're going to have to use the chain rule. And the chain rule says, first we take the derivative of natural log, and then we multiply by what we get if we take the derivative of the inside function. The derivative of plus 1 is 0, but the derivative of 1 over n squared is negative 2 over n cubed. In the denominator, also the derivative of 1 over n squared is negative 2 over n cubed. That's what it looks like after applying L'Hopital's rule. Notice that that factor cancels with that factor. And I'm thinking about the limit as n approaches infinity of 1 divided by 1 over n squared plus 1. What happens to the 1 over n squared as n approaches infinity? 0. So that's 1 over 1, so it's 1. Cool. Since L equals 1, we know that my original series, the one I care about, converges by the limit comparison test. So maybe you picked up on it, but just like a lot of things in calculus, the trickiest part of this problem is like knowing what series to compare it to. It kind of reminds me of like, kind of reminds me of like U substitutions, you know, like the trickiest part of a U substitution integral is like figuring out what U that we need to select before we can make the substitution and solve the integral. Same kind of deal. It's like you might be hitting your head against a wall for a while if you've got a limit comparison test question, because you might just be sitting here thinking, what the heck series should I be using to compare against to tell if this is going to work? But yeah, just to recap, if you get a real number between 0 and infinity that's not 0 and it's not infinity as the limit of the ratio of the terms in two different series, then those series are either going to both converge or they're going to both diverge. In this case, they both converged. Questions? Okay. This one looks very similar, but it's a little bit different. So the series we care about has terms that look like natural log of 1 over n plus n. We don't know if this converges or diverges. What series could we compare it against? Nice. 1 over n, that's perfect. And when we do this, we take, actually, first of all, let's investigate really quick and say, what happens to the series 1 over n?
Converges to 0.
The sequence 1 over n would converge to 0, but the series would, it diverges. How do we know that this diverges?
The geometric, it's either geometric or telescope.
It's not geometric. It's not telescoping.
P series because n
Oh,
or
and
p
this one.
equals 1.
Yes, this is the p series with p equals 1. That series has a special name. It's called the harmonic series. The limit test is going to have us, or the limit comparison test is going to have us take the limit as n approaches infinity of an divided by bn, and that means we take natural log of 1 over n plus 1 divided by 1 over n. And in the limit, we get very good. We get 0 divided by 0 again. So we apply L'Hopital's rule, and we take the same limit with the derivatives of the top and the bottom. And just like before, the numerator is going to require the derivative chain rule. So we take the derivative of natural log, and then we multiply by the derivative of 1 over n. In the denominator, we also have the derivative of 1 over n. And then you see those are going to cancel. So we're thinking about the limit as n approaches infinity of 1 divided by n plus 1. And then we write, since L is equal to 1, this original series we care about converges or diverges? Diverges. According to the limit comparison test. Okay, we got 12 minutes left. So you've got a page of homework problems in front of you, or review problems. Let's keep working examples for the next 12 minutes. Let's get another example in here. You pick one and you tell me what it is.
Going DK. Which one was it?
Oh, I don't care.
Okay. How about 1 over n factorial? And then n equals 0.
Okay. Interesting one. So this series is going to be 1 over 0 factorial to start, and 0 factorial is just 1. Then it'll be 1 over 1 factorial, which is just 1, and then 1 over 2 factorial, and 1 over 3 factorial, and 1 over 4 factorial, and so on, right? But let's call A 1 over n factorial. And the trick is we have to find a b to compare it against. Using either direct comparison or limit comparison.
What if you just did 1 over n?
So if you just did 1 over n is a converging or diverging series?
Converging. Oh wait, no, diverging.
It's diverging. And is 1 over n factorial less than or greater than 1 over n? Less than or greater than? Yeah, that'd be less than. Because like 1 over 5 factorial is 1 over 120. 1 over 120 is less than 1 over 5. So if my original series is less than this comparison series, and the comparison series diverges, this is not going to be, it's not going to work to use a direct comparison test. And you could try a limit comparison test, but the limit is going to be 0 in that case. And so the limit comparison test wouldn't work in that case either. It's a good guess. I'm not trying to discourage you. And the reality is, like, when you're taking your test and you've got to come up with these, you probably will try 2 or 3 different possibilities before you land on one that's going to work. I've got an idea. What if we compare it against 1 over n squared? So here's what I'm thinking. Is that n factorial is going to be greater than n squared for all n greater than, let's see, 1, 2, 3, 3. You know, it's true that 0 factorial is greater than 0 squared, and 1 factorial is the same as 1 squared, and 2 factorial is actually less than 2 squared, and 3 factorial is less than 3 squared. But once you get up to 4 factorial is 24, 24 is greater than 16, 5 factorial is 120, that's greater than 25. Because when you square a number, you're just multiplying it by itself, but when you have the factorial, you're multiplying by every single number, counting all the way down to 1. And so that means an is less than bn for all n greater than 3. And remember, we can neglect the first 3 terms, n equals 0, n equals 1, n equals 2, because the starting terms of your series, they don't determine whether or not your series converges or diverges. You can neglect as many terms as you want from the start of your series, and it does not affect convergence. So specifically, an is less than bn, and so am I trying to show that bn converges or bn diverges?
Converges, I think.
Converges, yeah, because if the bn series converges and an is less than bn, that would show that an converges. So the series we're looking at is the series 1 over n squared Does this one converge or diverge? It converges. How do we know?
P-series.
Yep, because it's a p-series with p greater than 1. And then we say my original series converges according to the direct comparison test. So this time we didn't need the limit comparison test because we found a series to compare it to directly.
Should you always try the direct comparison test first, and then if that doesn't work, divide them?
Yeah. And you don't necessarily have to write this on a test. I'll understand if you understand that it doesn't matter whether I start from n equals 4 or n equals 0. Both of these are going to converge because you can neglect finitely many terms. And it doesn't change convergence. You are not allowed to neglect infinitely many terms, right? Like you can't neglect every other term or something like that. That would definitely change whether your series converges, but you can neglect a finite number of terms and it won't change. Okay, 3 more minutes. Got another one you want to see? And work it super fast, super fast.
You could do n over n plus 1 parentheses 2 n minus 1, or 2 to the n minus 1 power.
Okay. All right, that is a lot going on. Okay, so let's compare this one to a much simpler series 1 divided by 2 to the power n. And remember, that's the same thing as 1 over 2 all raised to the power n. This is a geometric series with r equals 1/2, which is absolute value less than 1, so it converges. I know my B series converges. For this, I think we're going to need the limit comparison test. So we take the limit as n approaches infinity of the ratio an over bn. So that's going to be the limit of n divided by n plus 1 times 2 to the power n minus 1. And then also in the numerator, we're going to have 2 to the n because we're dividing by the bn. In the limit, this is going to be n over n plus 1, and the limit of 2 to the power n divided by 2 to the power n minus 1 is just 2. And so that's 1 times 2, that's 2. So since L equals 2, my original series that we care about converges according to the limit comparison test. So this is one where you just have to simplify it a little bit. You think, what would be simpler? Well, if I ignore some of the garbage and just think, well, the important part to me is this exponential. That seems like it's going to have the most influence on what happens here. I'll keep the exponential function, and I'm going to try to get rid of some of the garbage stuff that's floating around for my comparison series.